Well, you can go ahead and start whenever you're ready. There you go.
Okay, so it's my pleasure to introduce Christine Hatch for this Mass Environthon webinar. She's doing a presentation for us that relates most closely to our current issue for this year, which is looking at water resources and climate change in our communities. Christine is an extension associate professor at University of Massachusetts. She's in the geosciences department. Her research focus is on hydrogeology, the connection between surface water and groundwater in particular. And I know she's been a part of a research group that looks, it's called River Smart Communities, and it's research and education for New England communities around flooding issues. Flooding in New England towns is a big and historic issue. I also know that she's got a real commitment to young women in the field of science. I know she's involved with Girls Inc. And that she's a great spokesperson for geosciences to the larger community. So thank you for joining us, Christine.
Well, thanks so much for having me. This is, and I welcome anybody to throw questions in the chat or to just, I don't know if it's a webinar, so they're not allowed to ask questions. Is that right?
Yes, I believe so.
Okay, so if there's a Q&A or questions come into the chat, I'm happy to answer any of those as they come in. Feel free to interrupt me as we go. And I believe, do I have,
I'll disappear.
Power to share screen here. Yeah. All right, let's do that. All right, so can everybody see that okay? So, droughts and floods in Massachusetts, now what? So I'm going to talk about thinking about droughts and floods in Massachusetts, and you may not know this, but actually in October, we were in a stage 2, stage 3 drought in most of the state, which is kind of astounding to me, particularly because I've been working on a wetland restoration and it was just full of water at that time. So it was kind of shocking how much water was there. But I'll give you a little background in the form of thinking about our weather patterns in Massachusetts historically and whether or not we have droughts and floods often in New England. And then we'll look at the definition of weather versus climate. And then we can talk about droughts, and then we'll talk about floods and some of the resilience to both droughts and floods, and then some of the river smart work that we did and lessons that we learned from floods that Will led with in that generous introduction. So here in Massachusetts, we are really blessed by rain. We get a consistent amount of rain throughout the year, and that's really works well for agriculture in our state. We have up to 40 to 50 inches per year and 30 to 75 inches of snow, depending on where you are. And there really isn't a distinct seasonality to the precipitation. And that's really quite unusual to have precip all year long. It just happens to be our climate. And so if you look at the black skinny solid line there, that's precipitation, and it's kind of flat throughout the year because we get some precipitation every single month of the year. And then there's more potential evapotranspiration in the summer, warmer months. And if you subtract those two, you get some of these other curves as you're going along. But basically, it's pretty flat. So our precipitation is pretty flat. And then with the that turning, with the potential for evapotranspiration and the plants turning on in the summertime and the fall, then you have the streamflow runoff curve. And so you see a little bump when the plants turn off and we still get enough precip, but not enough evapotranspiration. And then the groundwater follows that trend, but it's a little bit more muted. It doesn't change as much. It kind of goes up and down a little bit throughout the year. So then if I now go back to that climate of Massachusetts graph, And we look more closely at where all these winds come from. So we have all of these different air masses that converge on Massachusetts, and different winds from different directions bring different climate and weather to us. So the winds that tend to lead to our droughts come from the northwest. Nor'easters, if you've heard of a nor'easter storm, those tend to be really dramatic storms that come, and they're really intense, lots of precipitation, often happen in the wintertime. Those come from the northeast, and they often lead to flooding. Hurricanes also lead to flooding. Those come from the southeast and the warmer air masses over the Caribbean and the Gulf. And then we get the most moisture overall coming from the south and coming up from the southern Atlantic. And all of those sum together to there being some precipitation all year round, but some of these are also associated with our extreme events that we tend to get. And so if you go into a national atlas kind of publication that the USGS put out, there's indices of floods and droughts that you can see. And so I pulled a bunch of these off for the ranked floods and droughts up to and including 2011. So I'm a little bit behind the times. I got to go get back in the atlas. But what you can see here is that periodically we have floods and periodically we have droughts. And sometimes they're statewide and sometimes they affect just a section of the state, and sometimes they affect multiple states. And so what I've highlighted here in blue are all of the major floods that have occurred, the biggest ones that are ranked in this atlas. And then in orange are the big droughts. And so all of the droughts, most of the droughts were statewide. Some of the floods were multi-state, and many of the smaller floods were just sections of Massachusetts. So now I'm going to look at some of these big flood years. So here's the top 5 flood years in Massachusetts in order of well, these are they're not actually, I guess these aren't the top 5. They're 5 that I'm going to talk to you about here, but particular flood years. So this one is a photograph from 1927. The big flood year was 1927, 1928, and this is the Housatonic River. And I don't know if you've ever been up to North Adams and know Mass MoCA and the museum there, but there's this concrete chute. It's a concrete canal that just goes through the middle of there. That's the Housatonic River, the Hoosic River rather, and it was that was built after this storm in 1927, 28, and there it is ripping through a package store, and it was then subsequently tamed. And it's actually, they're going to take that out and they're going to restore that river, but that's an ongoing project. Another big flood year was both 1936 and 1938. This one's a picture from 1938. So this event was what they call a freshet, or a rain on snow event. So you have all this snow sitting around on the landscape, and then you get a big rainstorm on top of that. And so you get all of the volume of water from the rain and all the volume of water that you melted out of the snow, and it really turns into a huge flood. And I'll just point out that in 1938, we did not have big flood control dams on the Connecticut River. So this was a lot of flooding around the region and affected a lot of the New England states, very widespread flooding. And subsequent to that, these big flood control dams were built further in the north and up in Quebec. And this kind of flood at this scale couldn't happen now. And that's, where is that one? Oh, this is in Ware, but there's similar photographs from this flood from Northampton or Springfield or downtown Holyoke. And here's a photograph. This is actually only ranked number 11, but it was pretty significant and it was in recent history. This is Hurricane Irene that happened in 2011. And some of you may remember that flood. This is a photograph of Route 2 that crosses the state east to west up near the Deerfield and the Cold River confluence. And on that hill slope there is a 900-foot long landslide, and then a 600 and a 700-foot long landslide. And those slides together closed Route 2 for several months. And the sediment that washed off the landscape in that flood event was so dramatic that it filled up the Deerfield River, flowed into the Connecticut, and then this plume of sediment came out of the Connecticut River into Long Island Sound, and that's what you can see from space in the photograph on the bottom. All right, so now transitioning over into drought years. So I just told you that we get lots and lots of rain, and it's easy to grow things and cultivate plants in agriculture in Massachusetts because we get rain every single month of the year, but we actually get droughts. And coming from the Western US where it's more dry than it is here by a long stretch, I was really surprised to find that we actually have big droughts in Massachusetts also. The largest of these was undoubtedly 1965, 66. And this is a photo of the pump intake from Quabbin Reservoir, which is massively large. And you can see how far the water has drawn way, 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 way down, like way below the pump intake in that year. And the impacts of that drought went on for up to 10 years, depending on what you're looking at. And then in 1981, this one I always highlight because I think it's kind of an interesting social experiment. The students had all come back to class, came to UMass Amherst in early September 1980. And after just 3 days of being at college, they sent all the students home because the town of Amherst didn't have water to support the campus. In 1985, this drought had the effect of the Massachusetts Wetlands Protection Act being passed as a follow-up to this to protect the rivers and ecosystems of the state. So this one had a really positive impact that has been amended and added on to over time. So here's a little timeline of some of these water quality regulations. And Massachusetts is a very early actor in terms of wetlands protection and water protection. So we have the Clean Water Act, which you are familiar with, passes in 1972. That's federal regulations. And then the Massachusetts Wetlands Protection Act passes in 1986. And then there's additional water quality standards and conservation measures that are passed moving forward in time that improve on that. In 2002, that's another one of these drought years. They also passed the Surface Water Management Initiative, and that's on my timeline as well. This one tries to tie the water use in the state by mostly private landowners to the flows in nearby rivers and maintaining a minimum flow in those rivers to protect those ecosystems. All right, so now I'm going to move on to a little bit about the climate. And in the simplest possible terms, thinking about climate on Earth is thinking about an energy balance. So we have energy that comes in and energy that goes out. The energy that comes in is energy from the sun, and then the energy that goes out is our outputs. And if those are out of balance, if the inputs do not equal the outputs, we either cool the planet or we warm it up. And as you know, we're warming up the planet right now, which means more heat from the sun is coming in than is escaping back out to the atmosphere. And this state of climate that we're in now is widely now referred to as the Anthropocene period. And this is where we, anthropods, humans, have a large measurable impact on everything on the surface of the globe, from the geologic record to earth temperatures to sediment deposits. You name it, we have an impact on it. And this is the Anthropocene, so it's now named for us. Global temperatures are increasing, and that is causing sea levels to rise. And both of those factors affect the hydrologic cycle. And we humans are largely the cause of this. So none of this is new. This is the state of affairs in the Anthropocene. We can look back in time. How do we know this? Because as far as we know, we've always been here. But before we were here, we can actually go back to some other kinds of records left on planet Earth and look at what temperatures used to be like and what levels of carbon dioxide in the atmosphere used to look like by going back with some sort of proxy record. That might be ice cores that have annual layers. It could be tree rings, cave deposits, all sorts of things you can use to go back in time and see these records. So once we can compare what the past used to look like and know how we've impacted the climate, we can try to make future predictions. And it actually matters what we do and how we behave with our emissions, and because those things affect the temperature, the precipitation, and the winds. Those are our weather and climate variables, but it also really ties into the number of extreme events that we see. So the monsoons, it affects the El Nino cycle, the conveyor belt of the saline and temperature circulation of the ocean waters around the globe, which affects all of our local weather. And then those in turn have impacts on the physical environment, including floods and droughts and sea level rise and coastal erosion and the melting of permafrost. And some of those feed off of each other. So if we take one of these factors, just temperature change, how does that affect the hydrologic cycle? So here's a little drawing of a hydrologic cycle. You have some mountains and water cycles around this diagram in the form of snow and ice, and river flows out to sea, evaporation, it comes back around again. And the short answer to this question is warm air is capable of holding more moisture. So the colder an air mass is, the less moisture it can hold. So if everything else is exactly equal in our weather system and nothing else changes, we only bump the temperature up a little bit, every single rainstorm that comes through now has more water in it, and so can drop more rain on a field. And so if we're talking about an agricultural field, for example, if the rain used to come and it was this light, gentle drizzle that was good for the plants, now that same rainstorm might drop a lot more rain, big fat drops. It might damage the crops. It might flood the crops. And it may not be quite as beneficial for agriculture, for example. And similarly, if a storm caused a river to rise up to its banks and then flow out to sea, fine, no problem. But now if we have more water in that storm and it's dropping more water all at once, now suddenly you get a really big volume of water in a really short period of time. And now your river floods over and floods into your town and washes out your bridges and that sort of thing. So here's a summary of ways in which the hydrologic cycle is changed by changes in temperature. So if you imagine the temperature over the oceans rises, then that increases the sea surface temperature, ocean heat content increases, that causes the oceans to expand, that causes sea level rise. The melting glaciers also cause sea level rise. And the humidity overall increases, and land surface temperatures also increase, et cetera. So for the northeastern US, including Massachusetts, some of these changes that we've seen, and in 2007, when this particular report was published, these were predictions. These are no longer predictions. These are definitely observations, and all of these things are happening. So what we see is less total snow. So we have more rain and less snow. We see that the area covered by snow in the wintertime is smaller, and that winters are generally shorter. We get a lot less pond ice, and the ice on lakes and rivers breaks up sooner, and the spring snowmelt happens earlier. We also get some funny warming and cooling shoulders on the beginning and ends of winter that can really wreak havoc with plants. We see more rain in the winter. The snow is more dense, which is to say the snow itself is holding more water. The reason why people like to live in my home, or ski in my home state of Utah, is because the snow has about 2 inches of water for every foot of snow. So it's really fluffy. And if you have 10 inches of water for every foot of snow, then it's dense and sticky and hard to ski through. So snow density increases with increasing temperatures. One positive is we get a longer growing season, but we might also get droughts in the summertime, making that harder to sustain. And then, of course, those sea surface temperatures and levels are rising, and the peak river flows happen earlier, and that can really change the signal for the different fishes that migrate in response to those peak river flows. So here's a graph showing these increasing temperatures across the northeastern states, and you can see that the most dramatic increase in temperature occurs in the winter. In the winter months is the most dramatic, but really you can see this across all of the seasons. So some of the consequences of having more rain and less snow are, of course, our winter tourism and recreation. And as a hydrologist, I think about the water, snow sitting on the landscape as water that's sort of stored in place as it's just sitting there, and then it is gradually released over time in the spring and filters into the ground, and you effectively have less time for that water to be stored there. The earlier, warmer spring means more mosquitoes. We've seen a lot more EEE come through, and Lyme's disease coming from the ticks that come out earlier. Spring flooding can be greater when that happens, and then the longer growing season. But also you see changes in the forest composition, and trees can't just pick up and move north when it gets too warm for them. They'll just start to die out, and then we have unhealthy forests. We also in this region see an increase in precipitation. And this trend is a little bit less pronounced, but nevertheless, it's still ongoing. And again, more of that precip is in the winter and spring, and it's coming in the form of rain instead of snow. So we see both increased temperatures and increased precipitation in our region. So that can lead to various impacts. We also see sea level rise, and in fact, off of our coast here in the Northeast in Massachusetts, the North Atlantic is the fastest rising sea level just about anywhere on the globe, for a variety of sort of peculiar reasons having to do with the way that the ocean is circulating and the fact that that our land is still impacted from having glaciers on it 16,000 years ago. So regardless of whether we have the high emission scenario or the low emission scenario, you take what used to be a storm that would happen on average every 100 years, and that storm is now happening every 1 to 2 years. And so what it means is not that that storm would happen once every 100 years, but that it has a 1% chance of occurring. And so now that same storm has essentially 100% chance of occurring every year. And it's slightly less in some other coastal cities, but Boston, and Atlantic City, those rates go down. And so other consequences of changing precipitation, and particularly that intensity of the precipitation. So remember that warm air is holding more moisture. So for the exact same rainstorm, we now have a lot more landslides and a lot more erosion because the ground gets saturated. And then you have, instead of one sand grain sticking to another sand grain and kind of holding the hill slope in place, they're sort of floating with water in between, and it's not very strong. And so it can just cut loose and the whole hill slope can come crashing down, causing landslides and erosion, flooding. We could erode our road embankments and blow out bridges and have flooding of towns and so forth, including, and the other thing is that our extreme events, because each extreme event is now more extreme and larger, there's a design storm is a storm that we use to predict the size of, say, a river flow and design a bridge accordingly. And now all of our structures that were designed for a certain size storm are now inadequate to really predict what we expect to see in terms of river flows. And so now all of our crossings are much more vulnerable to damage and being blown out. And in addition to the likelihood of having more floods, we're also more likely to have droughts. And this is sort of a peculiar thing, but what happens is everything becomes more extreme and the distribution of precipitation changes over the years. So we get more of it in the spring, more of it in the winter, more of it as rain, and then that leaves less moisture in the atmosphere to be distributed during the summer months, and we also get more likelihood of having droughts. And so that's leaves water shortages for crops and municipal supplies. So here we are. Now here's our floods up on the top, and here's our droughts, and they happen the same time. So this is the drought from 2016, and we were in severe drought in the middle of the state, and it got abnormally dry later. This looks pretty similar to the graph. If you flip the red part upside down, you'll see that's a pretty similar graph to what we had in October of this year for a few months. And there are all sorts of impacts from this. The 2016 drought was particularly pronounced because it happened during the growing season. So this is a Christmas tree farm that was failing because the little sprouts dried out. Some of the sweet corn was not doing well, didn't get enough rain. And it was really, really tough for the farms to have enough water in order to meet the demand for this drought, because a lot of our farms really just depend on the rainfall that's regular to that's generally regular to maintain their crops, and don't have a lot of deep groundwater wells or other sources for irrigation. And then this is a picture of the Ipswich River, which is one of the only rivers in Massachusetts that goes dry, but it has now been doing that with some regularity, particularly in drought years. And then some bears were finding other places to forage because they got thirsty and hungry, and came out and had that. So you can go to this. This is a really great website that I really like to go to see where in the United States, but then you can zoom in on the state of Massachusetts, our current stream flows, average, below average, above average. So if you want to see floods, droughts, or historical data or current stream flow, all of these are here at the Water Watch USGS website. You can get real-time data. So for whatever time that it was that I pulled off the screenshot, you can see that there's a bunch of, in fact, it might have been in the 2016 drought. You can see that there are a lot of places, particularly in the Central Valley of California, and then all up in New England was in drought in that particular time. Oh yeah, there it is. It looks like it was November 2016. And then the stream flows during that same period were also really low. So they're all little red dots, and those correspond to the droughts as well. But then you had some places that had excess stream flow and seemed to be in flood. And so you had some flooding in the middle of Texas, and you had some flooding up there in the Northwest, Pacific Northwest. Anyway, so it's a fun website, good resource if you want to see what current conditions look like. So this was, November 2016 when we were in drought. And so we had a lot of our streams that were flowing well below typical stream flow numbers. And similarly, there's that same drought map. And this one also got into the level 3 drought, which is extreme drought. And these are composite index values that the USDA and other organizations have come up with to really try to categorize all of the possible factors that could lead into a drought. So they take into account evapotranspiration and weather variables, as well as soil moisture and antecedent moisture that's in the air and the ground when they make these predictions. And this is another way of thinking about long-term water storage in the ground. This is actually a satellite, a NASA satellite that uses gravity to measure how much moisture is in the soil. So water has a particular density to it, and if water moves around, it will change the density of the shallow surface of the earth. And this satellite can detect those changes. So looking over time, we can see where water has been extracted over time, or where there's surface soil moisture. And this is another means of indicating droughts and super saturated areas. So this one is the surface drought indicator, and then if you go a little deeper, this is now the moisture in the root zone. And so, of course, this kind of information would be much more interesting to farmers, because soil will trap some moisture in it for a period of time, but eventually, if it's dry for a very long period of time, that will also dry out, and then the crops start to get stressed and die. And so in September of 2016, when we were in the middle of that drought, things were pretty dry in the root zone in Massachusetts and across the whole Northeast. And then if you keep going a little deeper, you can get into the shallow groundwater. So that particular drought was long enough and sustained enough lack of precipitation that it brought with it declining groundwater levels. And so this indicates now a bunch of that groundwater has left the shallow subsurface. And so this article was just highlighting the fact that these droughts take a long time to really develop and accumulate. And so it takes a long time for the groundwater to be used up by the plants and the humans on the land surface. So this one went back actually to 2013. And so now I just want to show you what we have, so a record of climate in the water cycle over time, and I'll highlight a couple of those big events that I talked to you about from the atlas in the very beginning. So we've got a few really big drought periods, and so this is a graph of anomalies, which is to say you take all the values of, I have 4 variables here: groundwater, precipitation, temperature, and stream flow. And I average them all together over this entire period of record from 1936 up to 2010. And then I look for times when things are really, really different from the average. That's the anomaly. So it's a change that's really, really different from what all of those other values say. And so these reflect times when we've had droughts and floods. And so the drought periods are here, this 1965-66 drought, and you can see that the groundwater was hugely depleted all the way down. It was a really big negative anomaly there. So groundwater was very depleted for a good, 6 or 7 years after the initial drought. And following that was also, the stream flow was also depleted for that same period of time. Precipitation, of course, was down because that was the initial cause of it, but it was sustained for quite some time. And temperatures were relatively cool during that drought. In 1981, temperatures were sort of average. Stream flow was a little bit low and the groundwater was low. And then if you go to the 2002 drought, that one has also a negative groundwater and stream flow anomaly and precipitation, but the temperature is high. And so you can kind of see the temperature is rising over the course, over time, and it may be producing more of these droughts over time, but the severity of the drought could even be worse now that they're hot droughts. And here's some of our wet periods as well from that same graph. And so these are highlighted there in blue. So this is just the precipitation minus potential evapotranspiration. So that's a good indicator for a drought. And then there's the stream flow on top of it. Here comes the groundwater. And then here you can see these trends. And what this is highlighting here is that we actually see an increase in the amount of groundwater. We see our groundwater levels going up. And so over time, this is a confirmation of our observations that we see an increase in precipitation, and that's actually causing our groundwater levels to rise in this region. All right, so I'm gonna zip forward a little bit to some of our River Smart informations before we run out of time here. But I'm gonna, well, we could give you this little quiz, but I can't ask you to answer the question, so you don't actually know. You can't really do it. But okay, so here's some of these droughts. So when we think about the impacts of floods and droughts in the Northeast, the local adaptations and mitigations are really of critical importance to how resilient we and our communities are to these problems. And this is where you can come in and work on your Envirothon project for this year, is really thinking about how do we build this kind of resilience within your community with respect to water resources and climate change. The short version of the geologic context within our state is that, unlike some of the Western states, we really don't have a lot of places to store a lot of water. So when we have droughts, we don't have giant aquifers that are places where we can store a lot of water in the geology under the ground. So our water reservoirs tend to be surface reservoirs and other storage ponds and things that we can use really just to get us through a short period of time. Something like Quabbin will allow us to be more resilient for a longer period of time, but then that takes a while to recharge as well. And this is due to our glacial history, which I'm gonna kind of skip over. So some of the ways that we can be resilient to droughts are thinking about some water use restrictions. So if you don't need to use it, don't use it, use less water. Things like watering lawns. I mean, I have to say, as a Western girl, I was pretty surprised coming here thinking, why on earth would you need to water your lawn? It's green all the time. Everything's green. It rains enough that the lawn stays green, but a lot of people water their lawns. So that's one of the first things to go. Your lawn probably won't die. Washing cars, that's another restriction. Any kind of like washing sidewalks or buildings or and swimming pools are some of these restrictions when they turn on the water use restrictions. So if they have guidelines like this. And then for farming, some of the permaculture techniques are really designed with water conservation in mind and water reuse. And so they'll use rain barrels to capture rain and then use that to water the plants. They increase the organic content in the soil, which means the soil can hold on to water for longer and it can hold more water. And keeping a lot of mulch on the surface and things that keep the surface of the soil away from the evaporation and keep the water protected in the ground also helps. It also helps to have low or no-till farming because every time you get in there and break up the soil, you break up the soil's natural ability to hold on to water and some of its organic structures that it builds. And then in permaculture gardens, they also use perennial crops, and so there's plants that are always in the ground. And so the more roots you have in the ground, the more you can protect the water in the soil. Also diversified crops. So now changing gears a little bit and going to flooding. So this is the stream flow map from September of 2011, which is when Hurricane Irene was the very end of August, early September 2011, and then when we were in the drought in 2016. So pretty different map when we were up in the high flooding area region of the curve to when we were in the red and much below normal time. So our definition for what it means to be river smart is to manage rivers and riverside landscapes, as well as our own actions and expectations, so that people and communities are more resilient to river floods. And specifically, these actions can reduce flood severity, reduce flood damage, and flood costs by understanding and accommodating the natural dynamics of rivers and river floods. So we learned a whole bunch of things from Hurricane Irene in particular. This is a photograph of the Deerfield River, and you can see there's a lot of sand and sediment that is not in the river. And that reflects where the river went during this flood. So it was a pretty huge flooding event, and the river just went out of its banks and went where it wanted to go. And we sometimes think of floods as just filling up the bathtub, but river floods are really not just inundation alone, because that water is carrying stuff, and it's carrying the sediment, and it's carrying debris, and it's carrying logs, and it's carrying everything else that it can pick up and carry along with it. And those materials can carve away at stream banks and can really quickly erode places that you might have thought were high enough to be safe. But if the banks can be eroded and the river is attacking that bank like a sandblaster with all of the materials carried in it, it can really do quite a lot of damage. So here's another shot of the Deerfield from above, near where it goes into the Connecticut River there. You can really see where all that sediment went. And where the material is eroded from upstream in the basin, eventually that will be deposited into these wide flat areas down below. Another lesson that we learned is that sometimes maps can be out of date or insufficient to show the flood risk. And so this is a new map that the USGS put out after Hurricane Irene. And another lesson we learned was when a river cannot access its floodplain. So if we've hemmed it in with a road or a railroad or some riprap or a steep wall, the force and the damage of the flood can continue for those downstream. Or alternatively, sometimes rivers can break through obstacles to reach the floodplain in a large flood. And either way, the result can be disastrous for human structures. So here's a river in Vermont during Hurricane Irene carving its way right on through the road because that's where it wanted to go, and then really destroying that house downstream. So river management sometimes doesn't incorporate the best river science. And so this was some of the efforts that we were trying to do, was to bring some of that river science into river management, thinking that these erosion and deposition hazards can be much more costly than just rising water. And so we want to try to get out of harm's way and get out of the way of the river. And one of the ways to do that is to map and designate a river corridor around the river and pick and find places where we might have settlements that are particularly vulnerable and move them to safer areas if possible, or protect them in place, but give that river plenty of room to move around and change its course as it needs to, and really try to discourage hard infrastructure inside that river corridor. And to do this in Massachusetts, it's something that we've been working to try to do based on some sound science. So in Vermont, they have this region mapped out, and they have very strict restrictions about what you can and can't do in the river corridor. In Massachusetts, we're just starting with this, and in Franklin County, in several places, they've worked to have some bylaws where they've mapped out a river corridor. They're really trying to get this onto the local maps and have the local all the local development have to abide by those standards. So rivers that can access their floodplains have scenic and ecological value, but by being able to access the floodplain in a high flow, they can go out there into the floodplain, fill up the floodplain, and slow down those floodwaters and provide resilience and a lot less damage downstream. So these were some of our recommendations that we came up with for RiverSmart as part of the lessons that we had learned. And it included mapping out these fluvial erosion hazards and upgrading our stream crossing infrastructure for these new climate change predictions of flows that we expect to see, and then support the community planning and support the regional intermediaries that are servicing these local communities. And so with that, I think I will stop and answer any questions if anybody has them. Thanks so much for your attention.
I'll just pop my ghost voice in and say to our attendees, if you you can either type a question in, or if you want to put something in the chat, I can elevate you to speak or participate at this point if you'd like to. Also don't want to put pressure on you if you don't want to do that. So anyway, thank you, Christine, for
thanks so
all
much.
of that. It was so much incredible information.
I have a, thank you, Christine. It was like a flood of information.
Nice.
So trying to work backwards here, you were talking about flooding and river corridors at the end. So say we have I have a river in my community. I'm an Envirothon team, but I don't know what its flooding history is, or I don't know what the controls are on it. Could I find maps of like the river corridor and flooding history, and who would I talk to in my community who would be concerned with these questions that the River Smart Communities project was looking at?
So if you live in Franklin County, you might be able to have some of those river corridors mapped, because some of them have been mapped. And that's unfortunately about it for official maps in the state. However, Franklin County did put out a fairly straightforward mapping protocol that pretty much anyone could do using a topographic map to try to map out their own river corridor. And so this is something that I think our Envirothon teams could probably do for their communities. That river corridor protocol is available on the Franklin Council of Governments website, and you can download it. If you just looked for FERCOG and river corridor, you probably would find it. And it goes through a series of instructions of how to look at a topographic map and identify where the river goes and changes its shape in such a way that you can identify roughly where you might expect a river to flood.
What about the FEMA maps, the Federal Emergency Management Agency? They have maps, right?
They do have maps. So if you, again, if you're in Franklin County, in that case, you're unlucky, because there's a big hole in the middle of the state that has not been mapped by FEMA. But for other parts of the state, there are good existing FEMA maps. Some of them are dated, which is to say they may not reflect the super accurate data, although there is this other thing that would be really, really fun to play with. And that is our state geologist. So if you go to Massachusetts Geologic Survey, has taken the LiDAR imagery from the entire state and made maps out of it. And I think you can access those and download that. And what it is an incredibly accurate topographic map, way, way, way more accurate than any of the regular topographic maps you can get, like down to resolution of a meter. And you can really see these landforms terrifically well. So that is available for the entire state.
So here's a question. Are there any predictions for the 2021 flood or drought season? Did the 2020 hurricane season affect Massachusetts as much?
I didn't see a ton of flooding. No, it wasn't super big. There's a guy that I always go to, Michael Rollins is my local weather guy. And he seems to know kind of what the what the almanac says for the year of whether this is going to be a big precip year or a small precip year, and I haven't asked him yet this year. But he always knows. He always has his finger on the button. I'm like, Mike, what's it going to be this year?
But one of the things that you did say was that what used to be something that had like a 2% chance of happening now has a greater than 50% chance of happening, so that any predictions could be wildly inaccurate or not.
Right. It's really tricky because if you look at all of the stream flows over, if we're just talking about stream flow, if you look at all of the stream flows over time that we've been recording them, you could say on average, there's a flow, what they call the 2-year storm is sort of the bankful flow. It's the one that goes up to the edges of the banks. And that happens once a year on average. And then these bigger flows that happen less frequently, you could say, well, we'll have a bigger one maybe every 5 years and a bigger one than that every 10 years. And the problem is that because all the storms tend to get more intense with climate change, those predictions are off. And so it might happen once every 5 years, but you might get one of those size storms every year now.
So one of the things that we've talked about in Envirothon over the years, as you know, I forgot to say, Christina's been working with us with Envirothon for what, 8 years now, 10?
Since I've been at UMass, yeah. Probably.
I latched onto it right away.
Hasn't let me go yet.
But so one of the things, if you have more extreme weather events, more opportunity, more possibility of flooding, more possibility of droughts, then the question for each Massachusetts community, which may have agriculture and may have cities with impervious surfaces, and may have forests, may have reservoir, whatever. So how do you kind of buffer the highs and lows? And one way, as you mentioned in the presentation, is that you can build dams. That was what we used to do. Now we're talking more about kind of using natural systems like wetlands to buffer highs and lows in the water, in the landscape. Or maybe we need more beavers to wetlands.
Beavers are making a comeback in Massachusetts. Yeah. It's a big deal. It's no joke.
But any thoughts about how to look at your landscape that way? How we might get creative with buffering for highs and lows?
Yeah, so it depends on what your desired use is, of course, what your best buffer is. But for a farmer, probably the farm water use is the most intense and the most demanding in terms of like, you got to have it now and you got to have it or your crops are going to die. The single best thing that a farmer can do is to increase the soil organic content, because that automatically stretches out the amount of time that the water stays in the soil. So that's, and it increases crop productivity for the most part. So that's kind of a huge win. And it also stores carbon. So it's something that solves the climate change problem, solves the water and the soil problem, and increases crop productivity. So that's kind of a no-brainer. That one's a really easy one to do. Other things to keep farms to have them last over some of these dry periods. Anytime you can have a cover crop and just keep roots in the ground and keep something on the land surface really helps a lot for storing water and withstanding some of those dry periods. For other water uses, it's tricky for human water use unless we can somehow store water. Obviously, water use reductions and higher efficiency appliances and water use, you know, like low flow shower heads that, and dishwashers that only use 2 gallons of water for a whole dishwasher load. And a lot of your clothes washers and things, a lot of those can use a lot less water. So there's high efficiency appliances. You can get a shower head that can only spit out 2 gallons a minute. You can have the toilet flushers that have, you know, the 2 different functions. So they have less water or more water. Water storage is tricky though. You know, unless you have a big cistern, you could always do the rain barrels. That's a pretty low tech, small storage thing. So when it rains, you know, you're collecting your water in a cistern or a barrel of some sort. And that could be on a very house by house or community by community basis thing. And then you can pull water out of that cistern when you have more need. Those are some ideas.
Yeah, I wanted to recommend to people to go back to those 2 resources, mapping resource or mapped resources that you presented to us. One was the Water Watch, USGS Water Watch, and the other was the GRACE, the gravity.
Oh, the satellite, yeah.
Satellite measurement. I recommend those because just for my learning about this topic, it's really interesting to think about water in the landscape, not just as one thing, but there's water in the root zone. There's also water in the aquifers, and those can go up and down. They're certainly related, but they can go up and down in different amounts in different ways. You might have no problem at all with your wells over the course of the year, but you may have wicked droughts and floods that affect the growing season. And I don't want to be too extreme about it, but there can be real differences that you know, a plant on the surface versus your water supply experience. So
that's right. And there are some places around the state where those resources are very well connected, where you do have your water well will go down when the stream flows go down, when you have a low precipitation and the soil gets dry. But there are other places where they're totally disconnected.
What kinds of places have
like Amherst actually is. Amherst is one of the weird cases where it's totally disconnected, and the reason why is because we're sitting on this giant lens of clay, and so the water supply for the town, well, actually the water supply for the town during that drought in 1981 when they sent the students home was in the form of a couple of surface ponds that had respectively about 5 days worth of water in them, maybe 2 weeks if you stretch it. So they've now gone to some groundwater wells. Well, these groundwater wells are down below a thick layer of clay, and it's a thick confining layer. So you can when you have a confined aquifer like that, it is kind of like a sponge, and it stretches a little bit, and so you can pull a lot of water in there over a period of time, and you won't notice any. In fact, you will notice zero impact on the surface. It's for the Surface Water Management Initiative. Amherst is one of the case study places where the surface water balance has nothing to do with what happens under the ground. That's unusual for Massachusetts. A lot of them are quite connected, but Amherst is one of those places.
So if I wanted to understand better, say I didn't live in Amherst, I lived in somewhere else. If I wanted to understand the geology that affects my water supply, who would I talk to? Where would I go for that information? It sounds very interesting.
Oh yeah, one of my favorite places to go is the MassGIS website, and you can play. There's an online mapper tool called Oliver, and you can go.
And Darthon uses that. Yep.
Yeah, and so you can go on there, and there are all sorts of layers to explore. You can look at the superficial geology, so that'll be a good first clue. So if you're looking for stratified drift, that is where your surface aquifers are. They're in the orange color. And then you can look at the water protection zones for any of the wetlands and waterways and river protections and wetlands protections. Those are all mapped out in the hydrology layers. the bedrock probably won't tell you too much about your water resources. There are fractured bedrock aquifers, but probably the dominant water resource that is impacted by surface processes is going to be in the glacial layers in the surface geology.
I'm hogging your, I don't know if there's any more people who want to put a question in the chat. We're just about at our, oh, we're actually a little past our
You
time.
just had too much fun asking me questions.
I have one more I wanted to draw people's attention to, which you mentioned a couple of times, the Surface Water Management Initiative. My understanding from George Zoto, our DEP committee member, is that that initiative is significant because it requires us, I may be wrong here, but it requires us to, or focuses our attention not only on the human uses of the water, but how the ecosystem uses and needs the water, and that we have to take that into account in our water use restrictions and that kind of thing. Is that?
That's right.
Yeah.
And it essentially uses municipal groundwater extraction as the means for maintaining stream flow.
Oh, so it tells towns your stream flow is too low, you got to stop drinking so much water?
That's right. And it's a more complicated formula than that, but that's approximately how it works. And you can get
that could be politically difficult.
I would think so. I haven't heard a ton of backlash about it, except when it was initially coming into play. But it's kind of interesting because you can get credits for different kinds of things. And one of the things that we thought would be a good idea, and I don't know that this has come to pass, but we thought it would be a good idea would be to ask that things like connecting a river back to its floodplain and restoration work like that improves the ecosystem and improves the river health should be counted as a credit, because you get credits for certain things that you do towards allowing your town to extract more water. And that seemed like something that would be really worthwhile to push for.
Right. Any other participants have questions, or this has been so cool. Thank you, Christine.
No worries.
One more question I had was about this connecting rivers back to their floodplains, and that you showed a kind of a drawing of a valley, a kind of typical valley in western Massachusetts, with the towns were all built right down by the river because that's where the power was, right?
Yeah, right.
And they did take flooding into consideration to some degree, but not the flooding that we have now, which can be because of climate or it can be because of impervious surfaces upstream. But it's one thing to say if we were a Native American community and we're moving around the landscape, that would be one thing. It'd be easy to say, let's let the river run its natural course. But when we have property ownership down by the river, valuable property, how do you talk to a community about changing the patterns on the landscape to let the river be run its own course? I mean, that must be really hard to talk about. Who does that talking? To planning boards in town, or?
Planning boards can do it. You usually have to get to a really, really, really high threshold of danger before you can talk about planned retreat and removing people from really the riverbank and the most valuable properties along the river. However, there's sort of a an accommodation that you can make for your river. So let's say you have a small downtown that is historic and you really want to preserve it, but it was built as a mill town, and so it's right up along the river's edge there. You can have the river in a chute for a short period of time, but if you take away the space for that river to spread out for this little chunk, you have to give that space back somewhere else. And so the way Vermont deals with that, because they have a lot of these little towns as well, is that they, in the planning of the river corridor, if they say, all right, for this river, the river corridor has to be 100 feet wide, but when we go through downtown, we only have 50 feet. So once we get through the downtown, now we're going to give the river 150 feet. We're going to give it this really wide area where it can move and spread out and accommodate all that extra built up energy that it accumulated as it went through our downtown. And then, and then you just armor your downtown a lot, and you figure, you're going to restrict the river through this one section, and you're going to say, nope, river, you're going to have to stay here, but only for this limited place, as long as you give it some room to expand and dissipate that energy downstream.
That's very cool to think about. I like to play with water in the sandbox, as you know.
Yes, I do. Sadly, we can't do that right now.
Yeah. So that if you have a chance to play with water in the sandbox, you can get a sense of how this could work. Yeah. Well, I think we should let you go. Thank you for staying. Those are my questions.
Well, my pleasure, and thanks so much for the invitation. As you know, I'm always happy to do it.
Yeah, it's great. Okay, it's good to see you.
Likewise.
Thank everybody for joining us. Yep.
You bet.
Bye-bye.